No, it's my radio. Sorry about that. Hello? Would you like to switch out one? Would you like to switch out one of your adapters, or?
Well, no, I have only one. It doesn't even pick it up.
It doesn't.
I just bought it.
And it doesn't even recognize it.
Yeah,
you can try, but it doesn't work. Let's just give it a shot. Let's give it a shot. But these are adapters. Some of them I noticed that I've gotten these, and some of them doesn't. It just doesn't.
Make sure people use them, because otherwise the remote viewers won't hear the question. They think they don't need it here, but kids hear the answer. And if they don't use it,
Or
the presenter should repeat the question.
Yeah, sometimes you have to buy them from
If they remember. Okay.
Everything else.
We have the other room doesn't turn off.
Right.
You know what?
Yeah, thank you.
Again, we have to go with the setup now because it's time to.
Another adapter.
If you want to, if you try to.
Come up with it. Let's try. It's the third one. Otherwise, we should just start the session.
So what the other?
Recognize it.
Oh, nice. Let's try.
So you want to get going about the wire, right?
We need, okay, we'll have keep having problems, but.
All right, sorry about that.
Okay, are you ready? I'll introduce you.
Yeah.
Okay. Hi, everybody. Welcome to the first talk of this session. We're going to be having Yanlin Chen talk about some upper and lower bounds for linear regression. Okay, take it out.
Okay, thanks everyone. I'm Yanlin Chen from CWI Amsterdam. Today, I would like to introduce you our recent work, quantum algorithm and the lower bounds for linear regression with non-constraint. Sorry for the device issue. Yeah. Okay, so this is the joint work with Ronald from CWI, University of Amsterdam, and the QIP. So let's get started. So first of all, let's talk about what is this square linear regression. So our setup looks like this. Yeah, it disappeared. Yeah. Sure. No? Oh, nice. Yeah, work magically. Yeah. Okay. Okay, so we will assume that we receive lots of points and its corresponding label, and our goal is to fit lines through those points. You can also consider this line is actually a d-dimensional vector. Yeah. Come on. Okay, so you can also consider this line is a d-dimensional vector, and how good this line is to measure by its
Yeah, changing the side. Also, where's the echo coming from?
Nice.
Okay.
Thank you. Okay, so how good this line is measured is by compute its squared loss. That is H transpose theta minus y squared. And because we will assume that our points are drawn independent and identically from a specific unknown distribution D, so what we really like to know is expected loss. But because this distribution is unknown, we cannot really access to these laws. So instead, we compute the empirical laws. This is the average over laws, square laws over our samples. And now we would like to introduce the problem, linear regression. So in linear regression, we would like to find the seed to minimize the empirical loss LS of seed. And in it's terrible.
Did you have a new adapter?
Sorry, I do apologize for the poor project.
About the adapter?
The adapter is fine. The problem with the connection.
But this is the problem. Sorry.
Okay, so in this talk, for convenience, I will assume that we will receive our input as a capital X as Y, and our capital X. I think this talk will last for over 40 minutes. Yeah.
Sorry.
Yeah, it's ridiculous. Yeah, okay. So we will assume that our input will be written in the matrix form. That is a capital X and the factor Y, such that the law of matrix X is typically XY, and the entries of Y is typically YI. And we are allowed to make queries to entries of capital S and Y. And if you make lots of queries to read, or we can present it in this way. Okay. So if you make lots of query to read out every entries of capital X and Y, then actually you have a cross-form solution for the linear regression problem. You can just compute the Penrose pseudo inverse of X transpose X and apply it to the X transpose Y. But there are some downsides for this issue. That is, there might be your answer might be overfitting and be even very dense, even if only few entries of your xi affect your label outcome yi. So how can we solve this type of problem? So in machine learning field, people find you can sort of solve this problem by adding some more constraint or equivalently regularize. So here is Lasso, regularize the linear regression. So Lasso is actually quite a popular and well-known problem in both machine learning field, signal process field, and the static fields. And this problem now asks you to minimize the empirical loss inside the L1 ball with radius B. But for convenience, we will just let our B equal to 1 here. And we call this type of constraint as L1 regularize, and this regularize will help sparsity of seed, and therefore reduce some overfitting and density issue. Yeah, but there is also a downside for this problem. That is, there is no closed form solution in general. So instead of finding the true minimizer for Lasso, we are now trying to find an epsilon minimizer instead. So what is epsilon minimizer? So epsilon minimizer is basically to find your theta inside the one ball, such that its empirical loss of theta is small compared to the true minimum. And this problem is actually quite well studied in the classical case. We know both upper and lower bounds. And in 2011, Ha-Zong and Karen provide the upper bound runs in d over epsilon square time. And at the same year, Cesar Bianchi, Shalev Swat, and Shamir provide D over epsilon lower bound for this problem. And please note that in this talk, when I talk about upper bound, I always means time complexity. While I talk about lower bound, I always means query complexity. And as a side project, we also has a new classical lower bound for this problem. That is D over epsilon squared. Yeah, it just done 2 weeks ago. Yeah, and but what we really want to address today is, can we has any content upper or lower bounds for this problem? Okay, so before we step into our result, we would like to first introduce our computational model. In our input, we will assume that they are all stored in the quantum readable read-only classical memory, that is QROM. And we are allowed to use a classical computer, of course, and it can run some quantum subroutines like maxima finding or amplitude estimation. And here we would also use a specific data structure called quantum readable classical writable classical memory, that is QRAM. And I know some of you might be very skeptical about this type of data structure, but the good thing here is we don't really use too many of them. And at the end, our goal, instead of outputting a quantum state kit theta, our goal is to output a classical vector theta. Okay? And our time complexity comes in the following. First of all, of course, the number of operations and the quantum gates, and also the quantum of number of queries to QROM and QRAM. And now this table is our result. Oh, shoot. Okay. Yeah. Okay. Yeah. So this table is our result. In this paper, we show both quantum upper and lower bounds for Lasso, and they are actually tight in D dependence and almost tight in epsilon dependence. Okay. And in the following 3 slides, I would introduce how our quantum algorithm works for Lasso. Sorry, just a second. Yeah. Yeah. So, okay. So let me do a quick recall. So basically, we want to solve linear regression problem, and we both wonder its upper bound and the lower bounds. So in our work, we provide both quantum upper and the lower bounds for this problem. Yeah, can I, every time you work in scale. Okay, good. Yeah, so you can see they're actually tight in D dependence and almost tight in epsilon dependence. Okay, and our quantum algorithm actually based on a classical confidence optimization algorithm, that is Frank-Wolfe algorithm, and that's how it applies to Lasso. So in Lasso, we will run a specific subroutine lots of times, say capital T times. And in each subroutine, we would like to find the vector phi, and it's minimized its inner product with the gradient of loss function of theta t, where theta t is the previous candidate. And after we find this vector, we will use it and the previous candidate to output a new candidate theta t plus 1. Okay, and please note that both our loss function and our domain are convex, so we are allowed to use convex optimization algorithm. And here is the picture for explaining how it works in each iteration. So suppose we have theta t, then we will compute its gradient, and then we will find the vector phi minimized in the product with this vector. And because we are now inside L1 ball, so it's typically a corner of L1 ball. Okay, and after that, we will use this vector phi and the previous candidate theta t to compute our new candidate theta t plus 1. And Frank-Wolfe algorithm guarantees us that it will help us to find the epsilon minimizer in only 1 over epsilon number of iterations. So it's quite fast. And also, because we are now inside L1 ball, to find such kind of phi, it suffices for us to find the coordinate of the largest entries of our gradient. Okay, and because it's typically a corner of L1 ball, so we know for each iteration, the sparsity of candidate is increased at least by 1. So we can sort of upper bounded the sparsity of our candidate theta t by the number of iterations. And the last thing is especially good for quantum algorithm, that is Frank-Wolfe algorithm itself is really, really robust against small errors. That is, instead of finding the true maximum, we are now allowed to find the approximate maximum instead. And now you might wonder how we can apply the quantum power on the Frank-Wolfe algorithm. And in our quantum version Frank-Wolfe algorithm, we don't really reduce the number of iterations. Instead, we reduce the cost per iteration. And here is one of our main results in our paper. We found that suppose we can prepare the quantum state ket theta t, which encodes its entry as an amplitude in front of the computational basis. Then we can use that to estimate entries of gradient with additive error epsilon in time 1/epsilon. And after that, we can run the quantum maximum finding algorithm to find the largest entry of our gradient. And you will take time square root of d and the square root of d applications of the first subroutine. So at the end, the cost per iteration will be square root of d over epsilon. And now you might raise another question, that is how we can have such kind of quantum state. So here we use a data structure we called modified KP tree. And this is a QRAM data structure for state preparation. And the KP is for crediting Karanidis and Prakash. And there are lots of good things for this type of data structure. First of all, if your seed is quite sparse, then you don't really need too many of QRAM bits to control this type of data structure. And the second is, if you have this type of data structure, you can help you to prepare the quantum state ket theta t in only O tilde1 time. So it's quite efficient. Yeah, but there is also a downside for this data structure, that is you use QRAM. But the good thing here is we don't really need too much of that, so it's relatively okay. And in our paper, we propose a variant version of KP3, which can help us to update our theta t to theta t plus 1 efficiently. And our trick is especially to store an extra scalar at the root. And in that case, when we want to update our theta t to theta t plus 1, we can modify this. We can modify the scalar at the root and then just modify one pass from the leaf to the root, and it suffices to update. Okay, I see. Oh, good. Okay, finally. Yeah, good. Okay, now you already know the cost per iteration for the quantum Frank-Wolfe algorithm. So we are now ready to show the time complexity from our quantum Frank-Wolfe algorithm. So again, here is the quantum Frank-Wolfe algorithm. As what I said, you will run the number of iterations 1/epsilon. And for each iteration, you will find the largest entry of your gradient. And here we use a subroutine to help us estimate entries of gradient. And after that, we will update our theta t to theta t plus 1 classically. And also we will update our KP3 for theta t to theta t plus 1. And so the total cost is quite straightforward. That is the number of iterations times the cost per iteration. That is square root of d over epsilon squared. Okay. And besides upper bound, in our paper, we also provide a query lower bound. And actually is square root of d over epsilon 1.5. And this is tight in d dependence. And our trick is to hide an index subset capital W inside the input matrix capital X. And here is an example how we hide such kind of matrix. So suppose we want to hide an index subset capital W equal to 1, 3. And please note that in our paper and this talk, our index starts from 0. Then what we do is to make the second and the fourth column slightly biased. Say the number of 1 is greater than number of -1. And for the rest of columns, it just balanced. Okay. And then suppose we have the kind of input capital X, and we said our Y is the O1 vector, and then put into the Lasso solver. Then the corresponds exact minimizer for the Lasso solver will put all its weight on entries of capital W. So it implies that an epsilon minimizer for Lasso can help us to reconstruct this index set approximately. So typically the larger entries will be your answer. So now you already see an epsilon Lasso solver solve a hidden set finding problem. So to show a lower bound for epsilon Lasso solver, it suffices to show a lower bound for this set finding problem. Okay. So now is our trick for showing the lower bound for the worst case set finding problem. So let's again see the definition for this problem. So we want to approximate an index subset capital W such that its input capital S each column sum is either to capital N or epsilon or balance that is 0. And the capital W is basically a set of index of columns whose entries add up to capital N. And if you see this problem carefully, you will find it can be decomposed into 2 problems. First problem is multiple item finding problem. That is, we would like you to find the 99% of W market item in a DB string with weight W. And it requires square root of D over epsilon quantum queries. And the second problem is Hamming weight distinguish problem. That is, ask you to distinguish Hamming weight capital N over 2 from capital N over 2 plus capital N epsilon. And this requires 1 over epsilon quantum queries. And thanks to the composition property of adversary measure by Belov and Lee in 2020, we know the worst case set finding problem has a low bound, which is the product of the above 2 problems. And that is square root of D over epsilon 1.5. And as what I said in the previous slide, we know an epsilon Lasso solver can help us to solve the hidden set finding problem. So therefore, a lower bound for hidden set finding problem implies a lower bound for Lasso. And in our paper, we also propose think about another linear regression problem with different non-constraint, that is REACH, the linear regression problem with an L2 regulator. And we used a similar argument to give a D over epsilon quantum query lower bound for this problem. And because we know there's a classical algorithm of REACH in D over epsilon squared, so there's no quantum advantage in no quantum advantage in dependence of D for solving REACH. Okay, so finally, we are finally into our summary. So in our paper, we consider about the quantum upper and the lower bounds for linear regression with non-constraint. So we consider both Lasso, which is the least square problem with L1 constraint, and REACH, this is square regression with an L2 regulator. And here is the table of our results. So in our paper, we provide both quantum upper and the lower bounds for Lasso and the quantum lower bound for REACH, and they are all tied in D dependence. Okay, so here's some open problem and future works. So first of all, as a theoretical computer scientist, we would like to tighten the, find the matching bounds. So we would like to tighten the epsilon dependency for both Lasso and the REACH. So it can be done by reducing the number of iterations by using some accelerated type of algorithm, like an accelerated Frank-Wolfe algorithm. We don't know yet, but we are still trying. And at the end, we also want to know the connection between Lasso and some machine learning problem like support vector machine. And that's it. Thanks, everyone.
So thanks to Yanlin for the talk, despite the challenges from classical technology. I think we can take a quick question while the next person is setting up.
Yeah, great. Thanks for the last talk. And I have a question regarding the lower bound. So you're saying that for Lasso and age regression, you are using the similar techniques to prove the lower bound, right? So, but we can see that the result, I mean, the scale in terms of the D is not the same. So yeah, why is that happening?
Okay, so the key issue is when we try to construct the corresponding instance in the L1 norm, we can sort of put in the L2 norm, we can sort of put more weight on our entries of our fact. But in the L1 norm constraint, that is Lasso, we can only put fewer items inside the D weights. Yeah, that's it. And that's also the reason we have a beta low bound for reach instead of for Lasso. Yeah.
Okay, yeah, great, thanks.